Yeah, hello everybody. Statistics, and so to speak, we are starting with the interesting part of statistics, estimating and testing. Well, estimating, doing it from a descriptive point of view, this we have already done, but until this, we could not talk about causality. So, given my data set, I find an average um, value of my data set, and in order to do then the forecast with a probability of 5% or 10%, I can rely on that my suggestion that the preferences of some guys are within some interval is true. So what we now at first want to do is, if we have a sample, then we ask very general, and this is not totally clear, or this is not obvious, or though there is no definite kind of way how to do it, um, that we want to find a, so to speak, good estimator for unknown parameters of our distribution. About this, we have talked when I introduced the normal distribution that, well, okay, the normal distribution is maybe quite often a good choice to take because of the central limit theorem. But in general, we don't know the exact distribution of our sample. And then if we have a data set, then we can ask, well, what would be good estimators in order to describe our parameters? And then if we have these good estimators, then we want to go to so-called hypothesis testing, that we formulate a hypothesis, and then due to our data set, what can I say about the probabilities that I have made a good estimation? So how shall we test? Via our random sample. Very important is that we have chosen a random sample. If you priorly select your data and you do not have any random sample anymore, then you are not allowed anymore to do statistics. This is maybe the mostly done mistake when you are doing statistics. You are allowed to select your data, but then you are only allowed to do descriptive statistics. Really, to talk about probabilities and something like this, then you definitely need a random sample. And it's a pity because we don't tell our young people this anymore, that there are many mistakes are done. So given this random sample, that our formulated hypothesis about the parent population is true or false. Because, of course, if you make a survey as a marketing instrument, asking people about their preferences, about them good or something like this, then you just ask 1,000 people or something like this, but you want to have an estimator for the parent population, maybe the whole population of Wilhelmshaven or something like this, but you are taking only a sample of 1,000 people. So, how does it work? Well, we have our parent distribution, but this is unknown. Then we choose our random sample. For example, ask 1,000 people. Then we are deducing from these sample estimators and we are testing our distribution about our parent distribution. Okay, so then we at first have to define what do we understand under a random sample. Well, this is just a part of the parent distribution. Again, 1,000 people out of the population of Wilhelmshaven. I think in some project work or something like this in other lectures, you make just a survey that you are asking. In general, all students, you write them an email, please participate here in our survey, and then you maybe got out of our 6,000, roughly 6,000 students, maybe 300 answers or something like this. And then these 300 is the random sample out of the whole population. Well, of course, since I do not ask everybody, then there will be, if I'm calculating something like averages and so, a difference between the sample statistics and the true population parameter, because these are unknown and I want to estimate them via my random sample. And of course, this has to be randomly selected. And again, this random chosen setup, this is quite often not carefully done. Think, for example, you make your survey and then you get your answers, and let's say 300 and 290 of these answers are quite reasonable for your point of view. And then you see, well, you have 10 outliers, some crazy answers. Well, actually, then you are definitely not allowed to just argue, well, these answers are not reasonable, and therefore I take these outliers out of my sample. You have just to deal with this, because if you look, for example, at the normal distribution, then of course, still here outside in these intervals, in these tails, there is also the possibility that you have these outliers due to your distribution. And although you don't like the answers, you are not allowed to leave them out. And this maybe is sometimes done. Well, if you leave them out, then you still can calculate a descriptive average and you can, of course, interpret it, but you are not anymore allowed to do this hypothesis testing. Because otherwise you cannot apply probability theory. Okay, so then let's go to some more detail. Well, what is an estimator? Very surprisingly, we choose as an estimator so-called point estimations in order to determine via this estimator the true parameter. And for this, very surprisingly, we of course take all our statistical parameters we have already used, we have introduced in our descriptive analysis. And this is in general our means, our averages, and for the volatility, we have the parameters of variance, standard deviation, or if you have a Bernoulli experiment with the outcome 0 or 1 or loss and success, then we are just interested in the relative numbers of successes, because then of course we know directly the opposite number has to be the losses, and therefore we quite often interested in proportion. Okay, actually this is nothing else than a special case of the arithmetic mean. Think, for example, you have 0 and 1 as outcomes, and then you say, let's say 0 8 times and 1 12 times, then the arithmetic mean would be 8 times 0 plus 12 times 1, and this is nothing else. 1 over 12 plus 8 is 1 over 20 times 12, and of course this is just the proportion of wins. And then the so-called higher moments, where remember x bar is sum over xi, variance is sum over the quadratic deviation, and then you can go to higher moments, and this is then called skewness. This would be roughly something like the deviation to the power of 3. And so you can go on to 4, 5, and so on, and this would be the higher moments. I don't know, have you talked in your introductory courses about, for example, skewness?
I don't think so.
Well, I don't think so. So, what I here have already given, this is the formulas for your estimator. How do I calculate them? Well, and then of course, in general, we calculate as an estimator. An estimator, this has now always our hat about above the variable. So this we calculate as the arithmetic mean over capital X. I have talked about this. Capital letters are chosen in statistics for random variables. And then this would be the definition for your general distribution for the random variable. And then you choose via your survey, for example, specific values. These are the answers of your students. Then you have specific numbers, and having these numbers you can calculate the arithmetic mean, and this is then the estimator for the true value of the parent distribution. Again, capital letters, random variables, lowercase letters, the concrete values. And the arithmetic mean of a sample is the estimator for the true mean mu of our parent distribution. Very surprisingly. Well, and then I already mentioned that the proportion is just a special case of the arithmetic mean. So the number of successes, k over n, this is then an estimator for the proportion of the true parent population, especially in Bernoulli experiments. Yeah, so these are, so to speak, the estimator for the mean, and then we move to estimators of the volatility, and there we want to have an estimator sigma hat squared for the unknown variance of our parent distribution. And there is something surprising, that if you go in your introductory course, there you have defined the sum over the squared deviations from the mean. Here we take the estimator, the arithmetic mean, divided by the amount of your sample, divided by n. And here we divide by 1 over n minus 1. We subtract one of the amount of the total sample. Again, have you already talked about this? I suppose not. I will later on in this lecture show you why this is the reason why we divide not by n, but by 1 over n minus 1. Be careful. Taking the, so to speak, descriptive variance 1 divides by 1 over n. And the reason for this I have qualitatively here already given you, because dividing by 1 over n minus 1 and not 1 over n, then we obtain a so-called unbiased estimator, and what we understand by unbiased, this comes in a minute. Yeah, because now, as I mentioned in the beginning, what is a good estimator? And these criteria, the answers for the question, what is a good estimator? These criteria were developed in the so-called decision theory just 150 years ago. So this theory is not that old. So, and at first we define the property of an unbiased estimator. An unbiasedness means, well, what we want to do. We want to have an estimator part deduced from a part of the parent distribution with which we want to estimate the true parameter. Well, we have randomly chosen our students. You just send the email with your survey to everybody. So then, just by chance, somebody is answering. So everybody who is answering, this is then for itself a random variable. So in general, then we can calculate the expected value of our estimator. Well, and then we want to have the property of our estimator that the expected value of the estimator equals, on average, the true parameter. So that we do not have a definite bias. So that we then say, well, that I really got the right answer, or that I got the definite value of the true parameter. This won't be the case. This would be only be the case by chance. But on average, the expected value of my estimator, then I should really reach the true parameter. So to speak, when I make at first a survey of 100 people out of 6,000, and then another one, and another one, and another one, let's say 4 times, then I got 5 different values of the estimator. And so to speak, when I then take the expected value, when I then take the average of these 5 samples, then I should be in the neighborhood. On general, the deviation to the right, to the left should be similarly high. So I think this is, of course, a good property which we should choose for the construction of our estimators. So unbiasedness. Then the next one is that maybe sometimes it is not possible to create such an unbiased estimator. Or what also can be possible is that although there is the construction of an unbiased estimator, but it is very expensive to get the data for these unbiased estimators. And so to speak, for the reasons of efficiency, we say if it's not possible or if it's hard to do an unbiased, to create an unbiased estimator, then I defined the so-called asymptotically unbiased estimator property. And this now means that if I have a sequence of expected values doing many surveys in a row, then I can take the limit for n reaching a very high number, or in the end infinity, that then the expected value of our estimator tends to the true parameter. So this is then asymptotically unbiasedness. As I said, in case of efficiency, that if I have an unbiased estimator, but to get the data for these unbiased estimators would be very expensive, for example. Then, so to speak, the second best choice would be then an estimator which is asymptotically unbiased. And then I have already talked about efficiency. And when do we call an estimator efficient? This we also definitely define. So efficiency means something like the accuracy of an unbiased estimator. And this accuracy, so the volatility around our true parameter, this we can measure via the variance. And then we can think of there are many unbiased estimators which I can define. And which one of these unbiased estimators shall I choose? Well, under the efficiency property, I choose then out of these many unbiased estimators that estimator which has the smallest variance. So we assume we have an unbiased estimator and then we take out of the sample of unbiased estimators that one which has the smallest variance. And also, I think this is a quite reasonable property because although we know when we take a sample that we are not exactly at the true parameter, we want to have in general a result which is not far away from the true parameter, and therefore it is a good choice to choose the estimator with the lowest variance. Yeah, and then we have the so-called consistency, and again, this is also a view on an estimator that in general, if we are redoing the experiment quite often, that we then want to be in the neighborhood of our true parameter. And this means if again we have a sequence of estimators, then we call this consistent for a given epsilon. This is a very small number. Just think of 0.0001 or something like this. That we then say if the absolute deviation of our estimator minus the true estimator is smaller than a given epsilon, that if we redo our experiment tending n to infinity, that then we obtain a probability of 100%. So again, that redoing our experiment that we are more and more in the neighborhood of our true value. Well, this seems like a little bit complicated, and I have to admit something I think you haven't seen in school. There you have in general talked about limits. I think you have done something like this, that lim of n tends to infinity, n squared plus 2n plus 1 over 3n squared plus n plus 2. Do you know what the limit of this function is? If n tends to infinity?
I have definitely done it in school, but I really don't remember anymore.
Well, you can just take the part with the largest exponent out of the brackets, and then you obtain n squared over 3n squared times 1 plus 2 over n plus 1 over n squared. And here we obtain also 1 plus 2 over 3n squared. And then, of course, these 1 over n squared terms tends to 0. We end up with a 1. These two cancels and we obtain 1 over 3. Have you done something like this in your math in school? Hopefully. I don't know.
Yeah.
I see what my kids are all not doing anymore in math in school. And this is really a pity because this is about competences for the future. Let's see what happens to our economy because of this lack of mathematic skills. Anyway, so this is the limit concept which you hopefully have seen in school, and this is then here the limit concept of probability theory. This is a so-called stochastic limit which we are here introducing, so that we are increasing n further and further and further. We know that we are then in an epsilon neighborhood of the true parameter. So, and of course, we also want to rely on our data that we hopefully in the neighborhood of our true parameter. So this would be then also a quite good property if our estimator has this. And then we have a more specific definition of consistency. Then we do not choose these stochastic limit, but we again define consistency with respect to our squared deviations, which we have used already quite often. So that we then say, okay, the expected value of the squared sorry for this, of the squared deviation should tend again against 0. And here we can then define the mean squared error, that this we can write as the variance plus a shift. And here, of course, we want to have that we tend again against 0. This is a more specific, which we can then practically more easier use than this general definition of consistency. Yeah, and then there is a last one, and this is a very general property, and this is called sufficiency. And sufficiency means that we are looking for an estimator that we have used all possible information. And so to speak, similar to efficiency, we want to have a sufficient estimator that we do not use too much information, which we just do not need. And yeah, this is maybe a quite general concept in order to explain it in more detail. Suppose that we have a data set with independently undistributed random variables. And now we take for an estimator a mapping of this data set whose values contain all information of the original data set. And then it is maybe possible that via this mapping we can reduce very high dimensional data sets to lower dimensions. Think, for example, again of a Bernoulli experiment. Then, of course, maybe throwing a coin 1000 times. Then this would mean we have 1000 data points. But the whole information which we need for that statistical description is just how many successes do we have. But we need only the number of successes. And this is a highly reduction, because also when we have the number of successes, we of course have also the number of losses. So we don't need the whole information for the statistical interpretation, but much less. And this then, so to speak, the proportion as an estimator is a sufficient estimator because it highly reduces the information we need. So proportion is an sufficient estimator. So, and with this properties, we can now start, or with these definitions, we can now start to do really statistics. And for this, why do we want to do statistics? We want now to talk about probabilities. What is a probability that I am in the neighborhood, that I have a good outcome? And for this, we define the so-called confidence level. And the confidence interval or confidence level is defined in the following way. We take just an interval where we assume that the true parameter is inside this interval, and then confidence level, we say we want to calculate these two limits in such a way that we can say, given the confidence level, for example 1%, then this would be 99%. Then we want to calculate the interval for which we can say that with a probability of 99%, this interval is overlapping the true value. So with probability 1 minus alpha, this could be also 5%, 10%. Well, what kind of confidence level you choose, this is not your or so to speak, you cannot deduce this, or you cannot say that I definitely have to choose 1% or 5%. You have to choose carefully this confidence level. And this is also something like a controversy in science, because very often one chooses 5%, and then many people, and this was also in one colloquium when a colleague just said, when I asked the student, why do you have chosen for your interpretation of the data an confidence level of 5%, then the other person said, well, confidence level is always 5%. And then I thought, no, this has nothing to do with statistics. You doing some probability experiment have to think carefully about a reasonable confidence level. Well, maybe quite often 5% is a good choice, but you always have at the starting point, think for yourself about the reasons. Is 5% really a good level, or should it be 1%, 0.1%, or even 10%? And also, quite often it is then said that with probability of 99%, we find the true value in the confidence interval. And this is also wrong, because these limits here, limits, remember how we created our estimators? These were some sums or something like this of our random variable. So the limits are by its own random variables. And therefore, we cannot say that with 99%, the value is within this confidence level, but we can say that this interval covers with 99% the true value, because the limits are by its own random variables, and so they can also just move in the second experiment a little bit to the right or to the left. Here the limits are also random variables. This is also in many textbooks wrong, when you find there that they say with 99% you find it in this interval. This is wrong. Okay, then of course we can define one-sided or two-sided confidence intervals. So maybe sometimes we only estimate, we only interested in a left border, or in a right border, or as at the former slide, a two-sided confidence level. Not confidence level, confidence interval. Yeah, and then of course we have to ask, how can we calculate these confidence intervals? And this of course depends on what we assume about the parent distribution. And if in general we don't know the variance of our distribution, we have to calculate this via the estimator for the variance. And again, of course, we choose the if we have here the parameter 1 over n minus 1, because then the variance is unbiased. And since our xi are random variables, in general, due to the central limit theorem, we can choose if our sample is large enough, roughly, one say rule of thumb, larger than 30, then you can just choose the standard normal distribution. And if you have a lower number in your sample, less than 30, then you have to choose the so-called student distribution. This is called student because in the beginning of the 19th century there was an Irish mathematician, I think. He has published a paper on this concept when you have only a small number in your sample, that you are then make a mistake if you still use the normal distribution, and he published his paper under the pseudonym of Student, and therefore it is called the student distribution. But we have as a property that we have to assume that our parent distribution is still normally distributed. And with this, we also take then, and this I show you in a minute, as we have done it in the normal distribution, we have to use the standard t-value for our calculation of the confidence interval. And additional, in order to be careful when I am allowed to do this, this also means, and hopefully you have done this in school or in your introductory courses, that your values, of course, also depend on is your sample size reaches your sample size the size of the parent distribution. Because think you have a parent distribution of 1,000 and then you picking 800 times within your parent distribution, not putting it back, then in the end you choose not, of course, out of roughly 1,000, but only out of 300 until, if your sample size is 800, until only 200, the last one you pick. And this, of course, changes your probability of the outcome depending on the outcomes which you had already before. And therefore, we also assume that you can choose this kind of estimators when your sample size is less than 5% of the parent distribution, or what also could be possible, throwing up to infinity in a coin, then of course you have no problem if the size of the parent distribution is by itself infinity. Okay, then we go into practice. How can we do this now? Well, we just can say, and this we have done in our little tasks in the last lectures, that we are just taking the standardization. And remember, we had our standardization equals z x minus mu over sigma. This we can then solve for our mu. So we obtain that sigma. Here we take our estimator, x bar minus x bar equals mu. Well, this is, so to speak, our volatility around the true value plus minus. And of course, we have here to calculate sigma of x bar, and this is sigma over square root of n. I think I have it still on the slides from the central limit theorem. Let's go back. Or have I? No, here I have it, that we then take this result that the variance of the arithmetic mean is just the variance of x itself scaling with the square root of n. I think this you have definitely done in your introductory courses. Here we are. Oops. Here we are. So then we end up at mu equals x bar oops, this is mu z, the other way around. Here should be a plus sign. So plus minus z times sigma hat, sigma hat over square root of n. Sorry. Yeah. And now we can take our definition. Let's go back of a confidence interval. The probability of the covering probability of our interval that we find within this our true value is 1 minus alpha. Now we have the concrete possibility to calculate the limits via this standardization parameter, and then we just say, okay, probability interval equals the confidence level. Yeah, and now we can calculate everything. This we get out of our sample. Z is the value of the standard distribution. Remember, this we can get out of our table. Here we can go back. This we have done the last times in the lecture. Here we have it. So, or even this is the better picture here. We just said, well, if we want to choose this confidence level of 5%, then we are here at the 95. So we have to insert for Z just plus minus 1.96. Okay. So where is it? Here. This is the standard normal distribution for the probability. And now, of course, since we go to the left and to the right, both together should be, for example, 5%, then it is plus minus 2.5 percentage points. So, for example, alpha equals 5%, then z for a two-sided interval is plus minus 1.96. Here we take the estimated standard deviation. This we can also calculate out of our sample. This is German sample size. And we can use the normal distribution. Okay, and then if we have a lower number, smaller than 30, then we are doing more or less the same. We only have to interchange the z value with the already introduced t value. And here you see something special, that the normal distribution, the shape does not depend on the number of the sample size. So we do not find any n here, but here the t value is dependent on the sample size. And again, we have to know that, assume that the parent distribution, this also, there you have to be careful when you are doing experiments. Please do not leave it out. Well, in general, sometimes you say that if you are doing this, that you do not directly assume that it's normally distributed, but at least that it is approximately normal distributed. So this is the value from the t distribution, and for this you also have tables, or in every software package, of course, you have formulas for the t values. But be careful, now it is depending on the sample size. And yeah, very surprisingly, again, due to the central limit theorem, if we start to increase n, then we are tending to the normal distribution. Or even you can say, since we are using software packages, in order to be more accurate, we can of course also choose the t-distribution of 2568. Although our sample size is larger than 30, we can, because it is easy to do it with a software package, still use the accurate calculation via the t-distribution. So this is only approximately normally distribution. So with software packages, one can, of course, use also the t-distribution for n larger than 30. So this is maybe from the historical point of view, because you can think of it is not that easy in the 1970s to provide the t-tables up to a number of 10,000. And also we have to admit, we are doing statistics. The error which you are doing by choosing the normal distribution, if you have larger sample size than 30, is far behind in the digits after the comma. Okay, so here I will show you the t-distribution, and here you see the black one is the normal distribution, and that if we start from n1, increasing it, that then the red distribution curve, the density function, tends in the neighborhood of the normal distribution. Okay, let's go on. And here, do not run away, but here you at least see how this student distribution really looks like. It is, yeah, of course, quite complicated. I don't know if you have seen this in math or in school. This is a so-called gamma function. And this is a general faculty. Remember, n faculty is 1 times 2 times 3 times n. And this, of course, you can also define for not natural numbers, and then gamma of x is something like an integral of, I think, t minus 1 times, well, I do not remember it. I have to look it up. Gamma function. Let's see how it looks like. So here we have it. Wikipedia is always a good choice. Oh, I'm almost right. So this is the tip and tip, and here we are. And put it in here. But of course, doing it by hand, this is quite hard to do it. But of course, this is doing today the computer for us. So let's go further. Then we can go just to the proportion. And remember, proportion is nothing else than the special case of an arithmetic mean. And then again, some conditions similar to n larger than 30. Then again, we calculate the interval similar to the other two kinds, that now we have a random normally distribution which we can use, and this is then again our sigma hat over n, a square root of n, sorry. And for this, of course, we also only need as an estimator the proportion. And this comes, of course, if you insert for this Bernoulli experiment with a success of 0 or 1, when you just insert this into the variance formula. And here, so to speak, then the standardized parameter looks actually the same as we had it before. So compare this with z is x hat minus mu over the standard deviation. Yeah, we are almost done, because then, of course, maybe we are not only interested in the expected value, But it could also be possible that we are expected in the variance. This we want to estimate. Well, and then it becomes even a little bit more complicated because the variance variance is a composite of squared random variables. Remember, it is defined the variance via the squared deviation from the expected value. Well, and then you can also show theoretically that such a kind of a variable, which is the sum of squared random variables, follows also a specific distribution if the x for itself are normally distributed, and this is the so-called chi-squared distribution. And I think one of you have also the topic of chi-squared estimation. Chi-squared distribution. Well, and then we just have to insert this definition into our definition of a confidence interval. Because then we say, okay, given now looking in the table for the chi-squared definition, we find the limits of our interval where we find y within this, but we are interested in sigma square, and so solve this for sigma square. And then, of course, we find sigma squared equals n minus 1 times s squared over y, and this is chi-squared distributed, and then inserting the values which we have looked up from the table of the chi-squared distribution, we then obtain the limits of the confidence interval for the variance. Well, and also this chi-squared distribution for n to infinity also tends to the normal distribution. Well, it starts a quite little bit different, but of course in statistics we are not really interested in experiments with n equals 1. But then you see for n equals 8 or 10, this tends more or less to a normal distribution. Tends also for n to infinity to the normal distribution. Okay, and don't be shocked. Again, this is the exact formula of the chi-square distribution that you also see it. And again, here you find the gamma function. And yeah, this we quite often use also, or we find this distribution also in other tests here for the test for the variance, but also for in the so-called chi-squared goodness fit. And this is one topic of your term papers. and the other one is the test, and this we will use here in our lecture for the independence. Remember the contingency tables. Until now, we have only the descriptive statement. Well, if the empirical probabilities differ from the theoretical probabilities, then we have a hint that maybe we have an not independent variables. But here now we also want to test this given some confidence level. Could we then rely on that our variables are dependent or independent? Okay, then that it was almost for today, but I will then upload for you again some tasks for next week. And in order to do this, look at the web page. Where is it? Statistics. There we are. Into the table, because of course we need also the numbers which we have already used for the normal distribution. Remember here, where is it? This was for the 5% confidence level. And then if you scroll down, then you see here that you have the t distribution. And then you see it is dependent on the number. And of course, we have to choose the confidence level. And here, if we take 0.97, let's say we have a sample size of 20, remember n minus 1, then looking this value up for 5%, then we have to choose here the 19, and this is 2.09. And there you see this little discrepancy to the normal distribution, since the normal distribution has here the value 1.96. So the t distribution is a little bit broader than the normal distribution. And scrolling, somewhere here, yep, there we have the chi-squared distribution, and there is also some difference. This I think forgot to say. Well, the chi-squared distribution is not symmetric anymore. So then, of course, to the left and to the right, we have different values. We could not just go the same direction from the average. And therefore, again, if we say we take 5%, then to the left in the tail, we have to have 2.5% of probability mass. And again, let's say we have n is 20 and minus 1 is 19. Then the left part of the interval we find at 8.907, and then we have on the right to go to 0.975 again here, and we end up at 32.85. In such a way, then you have to choose a table, or you can of course also use Excel or some other software package. There you just type in, say, well, I have a sample size of 20 and I have a confidence level of 5%, and then a chi-square distribution, pressing enter, and then you directly obtain the number. Why do I do it like this? Well, I have found in some bachelor colloquias that when I ask in the end, then the students, what have you done there? Chi-squared goodness fit, for example, or independence analysis. And then I ask, well, how did you obtain your confidence intervals? And well, then I got just the answer. I typed it in the software package, and the people do not really know what they have done. So I think today or tomorrow I will upload for you the other exercises where we then do the calculations for confidence intervals. Yeah, then thank you very much for today. And you have 1 week to do the exercises, and then we will meet on next Thursday. Thank you very much.